2019, astronomers pointed a radio telescope at a patch of empty sky, and they found something that shouldn't exist. A perfect circle, 1 million light-years across, glowing in radio waves, completely invisible to optical telescopes. No star at the center, no galaxy that could explain it, no known physical process that could produce it. They called it an odd radio circle. And since then, we've found more of them. And here's the thing that keeps astronomers up at night. These rings are enormous. One of them would swallow our entire local group of galaxies. And we have absolutely no idea what made them. Not a guess. Not a leading theory everyone agrees on. No idea. This is what that means. Welcome to Void Atlas. I'm your host, and today we're going somewhere genuinely strange. Not strange in the way black holes are strange. We understand black holes. Not strange the way dark matter is strange. We at least know what dark matter does. Today we're going into territory where the universe has done something, left evidence of it, and given us essentially zero clues about what that something was. Odd radio circles, ORCs. And if you've never heard of them, that's not surprising. They were only discovered 6 years ago. There are fewer than a dozen confirmed examples in the entire observable universe. They are, by any measure, the most mysterious large-scale structures we have ever detected in the cosmos. And they might be telling us something about the universe that we are not yet equipped to understand. Let's start from the very beginning. Let's start with the telescope that found them. The Australian Square Kilometre Array Pathfinder, ASCAP, is a radio telescope array located in the Murchison region of Western Australia. It consists of 36 dishes, each 12 meters across, spread across a remote stretch of outback that is deliberately chosen for one reason above all others. It is extraordinarily, almost uniquely, quiet. Not quiet in the human sense, though it is that too. Quiet in the electromagnetic sense. There are no cities, no major roads, no significant sources of radio frequency interference for hundreds of kilometers in every direction. The Murchison region is one of the most radio-quiet places on Earth, and that silence is exactly what you need when you're trying to hear the universe whisper. ASCAP was designed as a pathfinder, a prototype, a proof of concept for a much larger instrument called the Square Kilometre Array, which will eventually consist of thousands of antennas spread across both Australia and South Africa, with a total collecting area of 1 square kilometre. The SKA, when complete, will be the largest radio observatory in human history. ASCAP is the smaller sibling that comes first, testing the technology, mapping the sky, learning what's out there. One of ASCAP's key science programs is the Evolutionary Map of the Universe Survey, EMU. The goal of EMU is to map the entire southern sky in radio wavelengths, detecting and cataloging radio sources in unprecedented numbers and detail. When EMU is complete, it expects to find more than 40 million radio sources across the sky. Radio galaxies, pulsars, supernova remnants, quasars, the full menagerie of objects in the radio universe. And the vast majority of them will be things astronomers expected to find. Known categories, known phenomena. The radio sky is well studied. We know what's out there. Except it turns out we didn't. Not completely. In 2019, Ray Norris, an astrophysicist at Western Sydney University who leads the EMU survey, was reviewing early ASCAP data when something caught his eye. A circular object in the radio image. Faint, perfectly circular, roughly 1 million light-years across, with a galaxy visible at its center. Norris's first instinct was what any scientist's first instinct would be. Error, artifact, instrumental glitch. The history of radio astronomy is full of mysterious signals that turned out to be reflections off nearby aircraft, or emissions from terrestrial equipment, or subtle software bugs in the data processing pipeline. You learn, in this field, not to get excited too quickly. So they checked. They reprocessed the data. They used different algorithms. They pointed a different telescope, Meerkat, the South African radio telescope array, at the same patch of sky, and there it was again, the same circle, in the same place, unchanging, undeniable. And then they looked in every other wavelength they could access. Optical telescopes, infrared surveys, X-ray satellites. Nothing. Absolutely nothing. The circle was invisible at every wavelength except radio. It existed in radio waves and only in radio waves. This is when things got genuinely strange, because there is no known category of astronomical object that is a perfect, enormous circle of radio emission with nothing corresponding in optical or infrared or X-ray light. You can go through the entire catalog of known phenomena in astronomy, and nothing matches. Supernova remnants can be circular, but they glow in X-rays and optical light as well, and they're much smaller. Planetary nebulae are circular, but they're tiny by comparison and visible in multiple wavelengths. Radio galaxies can produce enormous radio structures, but those structures have jets, lobes, characteristic shapes. They're not clean rings. This was something new, completely, genuinely new. Norris and his colleagues published their discovery in 2021 in a paper in the Publications of the Astronomical Society of Australia. The paper described 4 circular radio structures. They had found more in the data. They named the category odd radio circles, and the name stuck, partly because it was accurate and partly because astronomers, like everyone else, enjoy a good acronym. The paper did something unusual for a scientific publication. It openly admitted that the authors had no explanation. They went through the possibilities systematically. Supernova remnants, inconsistent with the data. Starburst rings, inconsistent. Gravitational lenses bending radio light from distant sources, inconsistent. Artifacts of the telescope or data processing, ruled out. And at the end, they essentially said, we don't know what these are. We know they're real, we know they're large, we know they're distant, and we have no idea what made them. In the world of professional astronomy, this is a remarkable thing to say in print. Scientists are trained to be cautious, conservative, precise. Admitting complete ignorance about a new class of object in a major journal is not common. It means the object is genuinely, profoundly unexplained. Now let me give you a sense of just how large these things are, because I think the scale doesn't sink in immediately. Our Milky Way galaxy is roughly 100,000 light-years across. 100,000. An odd radio circle is roughly 1 million light-years across in early estimates, and more recent measurements suggest some could be even larger, potentially spanning several million light-years. That means a single ORC is 10 to 30 times wider than our entire galaxy. If you placed our Milky Way inside an ORC, it would be a small dot near the center. Our nearest major galactic neighbor, the Andromeda Galaxy, also a small dot nearby. The entire local group, the Milky Way, Andromeda, and all their satellite galaxies spread across several million light-years, could fit comfortably inside a single odd radio circle. And as of October 2025, we have confirmed only 8 of them. 8. In the entire observable universe, with all our telescopes pointed at the sky, we've found 8 of these objects. There may be more hiding below our current detection threshold, or in parts of the sky we haven't surveyed deeply enough yet. But right now, the known population of odd radio circles is smaller than the number of people who can fit in a small conference room. This rarity is itself a clue, or rather, it's a question. Are ORCs genuinely rare objects, or are they common but faint and hard to detect? Are they short-lived phenomena that appear and fade, and we're only catching a few at any given time? Or are they ancient and stable, but so faint and large that we've only recently built telescopes sensitive enough to spot them? We don't know. Here's something else that's deeply puzzling. 3 of the confirmed ORCs have galaxies visible at their centers in optical wavelengths. Not in radio. The galaxy appears in visible light only. And the probability of 3 separate ORCs each happening to have a galaxy at their center purely by chance is essentially 0. So these galaxies are almost certainly associated with the ORCs. They may even be the cause. But here's what makes this weirder. These central galaxies are not obviously special. They're massive early-type galaxies, the kind of large, elliptical, mostly red galaxies that are common throughout the universe. They don't have obvious jets. They don't appear to have active supermassive black holes in the ways we'd normally detect. There's no quasar, no obvious AGN emission in radio or X-ray that would immediately explain the ring. They look, at first glance, like fairly normal, massive galaxies, except for the enormous glowing ring around them. The relationship between the central galaxy and the ORC is one of the central puzzles of the field. Is the galaxy the cause? Is it a coincidence? Is there something about the history of this galaxy, something that happened millions or billions of years ago, that created the ORC we're seeing now? Let me walk you through the leading theories. And I want to be clear that I'm using the word _0 loosely here, in the sense of _1, rather than the scientific sense of _2. None of these explanations is fully satisfying. None of them explains all the observed properties of ORCs. They are hypotheses, best guesses, attempts to fit a strange observation into frameworks we already understand. The first hypothesis is the starburst explosion. This is the idea that at some point in the past, perhaps billions of years ago, the central galaxy experienced a massive episode of star formation. Not the gentle, ongoing star formation that happens in galaxies like our own, but a starburst, a rapid, intense burst of star formation affecting enormous numbers of stars across the galaxy simultaneously. Starbursts happen when galaxies collide or when large amounts of gas are suddenly funneled into the galactic center, and they can produce stars at rates hundreds or thousands of times higher than the Milky Way's current rate. When you form enormous numbers of massive stars very quickly, those stars live fast and die in supernovae very quickly. The combined energy of millions of supernovae, all going off over a relatively short cosmic timescale, can drive powerful outflows of gas from the galaxy. Not just gentle winds, but genuine explosions of gas, driven outward at hundreds of kilometers per second, expanding into the space surrounding the galaxy. This expanding shell of gas, as it pushes outward, creates a shock wave where the fast-moving outflow gas slams into the slower, cooler gas of the surrounding intergalactic medium. Shock waves accelerate particles, electrons in particular, to near light speed. And electrons moving at near light speed, spiraling around magnetic field lines, emit synchrotron radiation, which is a form of radio emission. A shock wave expanding outward from a central galaxy, producing a circular shell of synchrotron radio emission. That sounds like an odd radio circle. In 2024, a team of astronomers led by Allison Coyle of the University of California, San Diego, studied a galaxy at the center of one particular ORC using the Keck Observatory in Hawaii. They detected something remarkable in the optical spectrum of the central galaxy. An unusual amount of oxygen emission from gas, far more than normal. And, crucially, the gas was moving with a much wider range of velocities than expected, as if it was churning violently, disturbed by some powerful energetic event. This is consistent with a starburst-driven outflow. The gas around the galaxy is agitated, moving fast in ways that suggest something explosive happened here in the past. This discovery, announced at the American Astronomical Society meeting in January 2024, was significant. It's the strongest direct evidence yet linking a specific ORC to a starburst event. And it's given momentum to the starburst hypothesis as the leading explanation for at least some ORCs. But, and this is important, some ORCs, not all. The starburst hypothesis doesn't explain the pair of ORCs that were found sitting next to each other in the sky, with their centers separated by only about 2 arc minutes. The probability of 2 random ORCs appearing that close together by chance is essentially negligible. They must be related somehow. But a starburst in one galaxy doesn't explain why there's another ORC right next to it. So either ORCs can form in pairs, which would require some additional mechanism, or there are different types of ORCs formed by different processes, or both. The second major hypothesis involves the merger of supermassive black holes. We know that most large galaxies have supermassive black holes at their centers. We know that when 2 galaxies merge, their central black holes spiral toward each other over millions or billions of years and eventually collide. And we know from gravitational wave observations that black hole mergers release stupendous amounts of energy. A supermassive black hole merger, involving black holes millions or billions of times the mass of our Sun, would release energy that dwarfs anything a stellar mass black hole merger produces. Could the energy from a supermassive black hole merger propagate outward through the surrounding gas and create an enormous spherical shockwave? In principle, yes. The energy budget is certainly sufficient. A merger between two supermassive black holes could, in theory, release enough energy to drive gas outward for millions of light-years and create a ring of synchrotron emission on the scale of an ORC. The problem is that we haven't directly detected a supermassive black hole merger causing an ORC. We don't have a smoking gun. And there are aspects of the ORC morphology, particularly their remarkable circularity, that are difficult to explain purely from a black hole merger, which would be expected to produce a more complex, asymmetric energy release. The third hypothesis is something completely different. Some researchers have suggested that ORCs might be connected to fast radio bursts, those mysterious millisecond pulses of intense radio energy that we've been detecting for years and still don't fully understand. The idea is that whatever process produces fast radio bursts, if it occurred over a sustained period from a central source, might drive a continuous outflow that eventually forms a ring. This hypothesis is speculative and has not been confirmed, but it's on the table precisely because the universe keeps throwing up connections between phenomena we didn't expect to be related. The fourth possibility, and I want to be careful here because this one is at the more speculative end of the spectrum, is that some ORCs might be related to processes we simply don't have good theoretical models for yet. The universe has, more than once in the history of astronomy, produced phenomena that required genuinely new physics to explain. Pulsars, when first discovered in 1967, were so bizarre that the British astrophysicist Jocelyn Bell Burnell and her supervisor, Anthony Hewish, initially gave them the designation LGM-1 for Little Green Men, as a tongue-in-cheek acknowledgement that the signal seemed almost impossibly regular, almost artificial. It wasn't artificial, of course. It was a rotating neutron star, but it required new physical understanding to explain. ORCs may or may not require new physics. Most astronomers think the explanation will ultimately be found within existing frameworks. Outflows, shock waves, synchrotron radiation, processes we already understand operating at scales we hadn't previously considered. But the fact that no existing model fully explains all the observed properties of ORCs leaves open the possibility that something genuinely new is at work. And that possibility, however small, is one of the most exciting things in astronomy right now. Before I go further, I want to pause and do something I always think is valuable when talking about mysterious phenomena. I want to tell you what we know for certain and separate that clearly from what we're speculating about, because these two things often get blurred together in discussions of unexplained cosmic objects, and the blurring can make things sound more mysterious than they are, or less mysterious than they actually are. What we know for certain about ORCs: they are real. They have been confirmed by multiple independent telescopes using different instruments and data processing techniques. They are not artifacts. They are genuinely circular structures that emit synchrotron radiation at radio wavelengths. They are genuinely enormous, among the largest individual structures observed in the universe. They do not emit light at optical, infrared, or X-ray wavelengths at detectable levels. At least 3 of the confirmed ORCs have massive galaxies at their centers that are almost certainly associated with the ORCs. They are extremely rare, or at least extremely rare in ways we can currently detect. They are located billions of light-years from Earth, placing them in the distant universe. What we don't know: what produced them, how long they last, how they form, what specific physical process creates this particular shape at this particular size. Whether all ORCs share the same formation mechanism, or whether the category includes multiple types of objects produced by different processes. How common they truly are, given that our ability to detect them is limited by telescope sensitivity and sky coverage. Whether the central galaxies cause the ORCs, or are themselves caused by the same event that produced the ORC, or are merely located at the center by chance in some cases. This is an honest accounting of the state of knowledge. And I think it's worth sitting with, because it's genuinely rare to have an object in astronomy that falls so completely on the "we don't know" side of the ledger. Most things in the modern universe are understood, at least in outline. ORCs are not. And that's not a failure of science. It's science in progress. It's what it looks like when you discover something genuinely new. If you're finding this as fascinating as I am, if the idea of a universe that still has room for complete mysteries at the largest scales genuinely excites you, then I want to invite you to subscribe to Void Atlas. This is exactly what we do here. We don't just cover the things we understand. We go to the edge of what's known, and we stand there honestly, and we look out at what's still in the dark. Subscribe and come with us every week. Now let me tell you about one of the most intriguing individual ORCs ever found. Because in 2023, a team using the Meerkat telescope in South Africa found something that added a new layer to the mystery. They found an ORC that was located in the same field of view as a radio relic, a different kind of extended radio structure that forms at the outskirts of galaxy clusters when two massive clusters collide and create a shock wave in the hot gas between them. Radio relics are well understood. They're associated with cluster mergers, with physics we've studied for decades. But this particular ORC and the radio relic were physically connected. The two structures appeared to share the same region of space, in a way that was extremely unlikely to be coincidental. This suggested that the ORC and the radio relic, despite looking very different, might share a common physical origin. Both might be produced by shock waves. Both might be driven by similar energetic events at different scales. The ORC around a single galaxy, the radio relic around a galaxy cluster. This connection, if real, would be deeply clarifying. It would tie ORCs into a framework of phenomena we already understand well. Shock waves propagating outward from energetic events, accelerating electrons, producing synchrotron radiation. The same physics operating at different scales. It would mean ORCs are not as fundamentally mysterious as they seem, just an extreme version of something familiar. But it would also raise new questions, because if ORCs are driven by the same physics as radio relics, why do we see so few ORCs compared to radio relics? Radio relics are observed in dozens of galaxy clusters. ORCs, with equivalent technology, should be far more common if they form by analogous processes at galaxy scales. Unless ORCs require some very specific set of conditions, a particular mass of galaxy, a particular environment, a particular history, that makes them rarer than the general physics would suggest. Every answer in science opens new questions. This is not a failure, it's how knowledge accumulates. Let me talk about the telescope that's going to change everything about our understanding of ORCs in the coming decade. The Square Kilometer Array, the SKA. The SKA is the largest scientific instrument ever built by humanity. It will consist of two major arrays, SKA Low, an array of roughly 130,000 individual antennas spread across a large area of Western Australia, sensitive to low radio frequencies, and SKA Mid, a collection of 197 dishes in South Africa's Karoo region, sensitive to mid-radio frequencies. Together, they will have a total collecting area of 1 square kilometer. 1 million square meters of radio collecting surface. The SKA will be so sensitive that it could detect an airport radar on a planet orbiting a star 10 light-years away. It will be able to survey the entire radio sky to depths that ASCAP can barely scratch. And it will find ORCs. Many, many more ORCs than we currently know about. The current population of 8 confirmed ORCs is almost certainly a tiny fraction of the true population. ASCAP can only detect the brightest, closest, most prominent examples. The SKA will see far fainter structures at much greater distances. Current estimates suggest that the SKA could find thousands of ORCs, potentially tens of thousands, over the course of its science programs. And that's when ORCs will truly become a subject of precision science rather than curiosity. When you have thousands of examples, you can start doing statistics. You can ask, what are the properties of the central galaxies in systems that have ORCs versus those that don't? What is the distribution of ORC sizes and morphologies? How do ORCs evolve over time? Are there young ORCs and old ORCs? And can we tell the difference? Do ORCs cluster? Are they found preferentially in certain environments? Do they correlate with other known phenomena? Are they more common at certain redshifts, certain epochs of cosmic history? These are the questions that will actually solve the mystery. Not a single clever argument, not a beautiful hypothesis, but data. Lots and lots of data, allowing patterns to emerge, allowing theories to be tested, allowing the right explanation to distinguish itself from the wrong ones by its ability to match the observations. This is how science works. And with the SKA, this process is coming. Within the next 5 to 10 years, ORCs will go from "we have no idea" to "we have a detailed, quantitative, tested understanding." Or perhaps they will remain mysterious in ways we can't currently anticipate. That possibility is always open. Now let me take you somewhere that I think most discussions of ORCs don't go. I want to talk about what ORCs mean for our understanding of the universe's energy budget. When you produce a structure like an ORC, a shock wave expanding outward at hundreds of kilometers per second, pushing gas across millions of light years, accelerating electrons to near light speed across a volume larger than our local group, you are expending an enormous amount of energy. Where does that energy come from? If the starburst hypothesis is correct, the energy comes from supernovae, from the collective, explosive deaths of millions of massive stars. A single supernova releases energy equivalent to roughly 10 to the 44th joules. That's the total energy output of our Sun over its entire 10 billion year lifetime, released in a matter of seconds. Millions of supernovae together can release enough energy to drive gas outward at the scales we observe in ORCs, given the right conditions and timescales. If the black hole merger hypothesis is correct, the energy comes from the conversion of gravitational energy into radiation and outflows during the merger. Supermassive black hole mergers can release a significant fraction of the rest mass energy of the merging objects as gravitational waves and electromagnetic radiation. For black holes of millions of solar masses, this can mean energy releases in the range of 10 to the 54 joules or more. More than enough to drive an ORC. But here's the point I want to make. If ORCs are common, if the SKA finds tens of thousands of them, then the energy they represent is a non-trivial component of the energy budget of galaxy evolution. Galaxies grow, form stars, and regulate their own growth through feedback processes. Gas falls in, stars form, some stars explode. The energy from those explosions pushes gas back out, which regulates further star formation. This feedback cycle is fundamental to why galaxies look the way they do. Without it, simulations predict galaxies would be much more massive and star-rich than we observe. ORCs, if they're produced by starburst-driven outflows, are a part of this feedback process, an extreme part. Evidence that the feedback can operate on scales that extend not just to the edge of the galaxy, but far beyond it, into the intergalactic medium. Evidence that the energy released by a galaxy's star formation history can propagate outward for millions of light years and still be energetically significant enough to produce detectable radio emission. This has implications for how we model galaxy evolution. Current models of galaxy evolution treat the circumgalactic medium, the gas immediately surrounding a galaxy, and the intergalactic medium, the gas between galaxies, differently. ORCs, if they're produced by outflows, suggest that the energy from a single galaxy can propagate all the way from the galactic center to the intergalactic medium, linking these different regions of space in ways that our models may not fully capture. In other words, ORCs might not just be a mystery to solve. They might be a clue that our models of galaxy evolution are missing something important about how energy moves through the universe. And now, let me tell you about another dimension of the mystery that doesn't get discussed often enough: the magnetic field. Synchrotron radiation, the radio emission that ORCs produce, requires two things: fast-moving electrons and a magnetic field for those electrons to spiral around. We've been talking a lot about the electrons and where they might get their energy, but we've said relatively little about the magnetic field. The existence of a large-scale organized magnetic field pervading the volume of an ORC is itself a profound fact. Where does this magnetic field come from? The origin of cosmic magnetic fields is one of the deepest unsolved problems in astrophysics. We know that magnetic fields exist everywhere we look, in galaxies, in galaxy clusters, in the cosmic filaments of the large-scale structure. We can measure them through their effect on radio polarization, through the rotation of the polarization angle of radio waves as they travel through magnetized regions. But how these fields got there, how a universe that began with no magnetic fields developed the large-scale organized magnetic structures we observe, is genuinely poorly understood. For an ORC to produce synchrotron radiation, the magnetic field must have been amplified within the volume of the ORC, perhaps by the shock wave itself, which can compress and amplify pre-existing seed magnetic fields. But those seed fields have to come from somewhere, and the origin of the seed fields is connected to the broader question of cosmic magnetogenesis, the process by which the universe became magnetic. ORCs, in this sense, are probes of cosmic magnetism. Their radio polarization properties, when measured precisely, will tell us about the magnetic field structure within them. And that information will be valuable not just for understanding ORCs, but for understanding the broader question of how the universe's magnetic fields were generated and amplified. The SKA, with its extraordinary sensitivity to polarized radio emission, will be able to map the magnetic field structure of ORCs in detail, and those maps will be scientifically precious. There's one more thing I want to tell you before we reach the end of this journey, something that I think puts everything we've discussed in a broader context. We discovered ORCs because we built a telescope sensitive enough to see them, not because we were looking for them, not because theory predicted them. We built ASCAP to map the radio sky more deeply than it had ever been mapped before, and in doing so, we stumbled on an entirely new class of object that nobody had predicted. This is not unusual in the history of astronomy. The history of our understanding of the universe is, in significant part, the history of building better instruments and being surprised by what they show us. Radio astronomy itself began with a surprise. Carl Jansky, in 1932, trying to identify sources of static interference for Bell Telephone Laboratories, and discovering that some of the noise was coming from the center of the galaxy. He wasn't looking for the Milky Way's radio emission. He found it because he was building better radio receivers and pointed them at the sky. X-ray astronomy was born when physicists who were studying X-ray sources in the solar system pointed their detectors at the wider sky and found a universe full of X-ray emitters they hadn't anticipated. Neutron stars, black holes accreting matter, hot gas in galaxy clusters. The cosmic microwave background was discovered when Arno Penzias and Robert Wilson, engineers at Bell Labs in 1964, were trying to calibrate a radio antenna and couldn't get rid of a persistent, uniform background noise that turned out to be the echo of the Big Bang itself. And now, ORCs, discovered not by theorists predicting their existence, but by radio astronomers surveying the sky with new instruments and finding something that didn't fit any existing category. The universe keeps doing this. It keeps presenting us with phenomena we weren't expecting, phenomena that require us to expand our understanding, phenomena that remind us, every time, that our models of the cosmos, however sophisticated, are incomplete approximations of a reality that is more complex and more creative than we have yet imagined. This is what I find most beautiful about odd radio circles. Not the mystery itself, though the mystery is genuinely wonderful. Not the scale, though the scale is genuinely humbling. But the reminder. The reminder that the universe has not finished surprising us, that there are still first discoveries to be made, that we are not at the end of astronomy. We are, in many ways, still near the beginning. The Square Kilometer Array will find thousands of ORCs. It will also, almost certainly, find other things that have no name yet because no one has found them before. New categories, new phenomena, new first-time discoveries, new moments when an astronomer reviewing data stops, looks at the screen, and thinks, "What is that?" Those moments are some of the most important in science. And we are going to keep having them. The universe is going to keep producing them. As long as we keep building better telescopes and pointing them at the sky. We are at a remarkable moment in the history of astronomy. We are building instruments of unprecedented sensitivity. We are generating data at rates that would have seemed impossible a generation ago. The EMU survey alone will detect more than 40 million radio sources. The SKA will far exceed that. We will map the radio universe in a completeness and depth that will make our current knowledge look like a rough sketch. And in that flood of data, we will find things that change everything. Things that require new theories. Things that force us to revise our models of how galaxies form, how energy moves through the universe, how magnetic fields arise and evolve, how the large-scale structure of the cosmos came to be. Odd radio circles are the harbinger of that era. They are the first hint, caught at the very edge of our current instrumental capabilities, of a universe that contains phenomena we are not yet equipped to explain. And the proper scientific response to that hint is not to be unsettled by it. It is to be energized, to build better instruments, to gather more data, to develop better theories, to sit with the mystery honestly, without pretending to an understanding we don't have, and without giving up on the project of eventually achieving that understanding. That is what science does. That is what we do. This has been Void Atlas. I'm your host, and this video has been one of my favorites to make, because ORCs embody something I think about often. The difference between mystery and ignorance. Ignorance is the absence of questions. Mystery is the presence of questions you can't yet answer. ORCs are not a sign of ignorance. They are a sign that we're asking the right questions at the right depth. 8 confirmed rings in the observable universe, each one 1 million light-years across. each one glowing in radio waves and invisible to every other kind of light. Each one sitting around what appears to be an ordinary galaxy, waiting for us to understand what it went through to create such an enormous, beautiful, inexplicable halo. We'll get there. We always do. Subscribe to Void Atlas. New deep dives every week. The universe has no shortage of mysteries, and we are just getting started. I'm your host. Thank you for spending this time with me at the edge of what we know. Until next time, keep looking and keep wondering. The best questions in science are the ones that don't have answers yet. But before I let you go, I want to take one more detour into a corner of the ORC story that I find particularly compelling. Let me tell you about what it's actually like to discover something completely unknown in modern astronomy. Because I think there's a misconception that in the 21st century, with all our technology and data, genuine first discoveries are rare and happen in an orderly, expected way. The story of ORCs suggests the opposite. Ray Norris, the Australian astrophysicist who found the first ORC, wasn't having an extraordinary day when he spotted it. He was doing the painstaking, unglamorous work of reviewing survey data. Radio survey astronomy produces vast quantities of images, thousands of square degrees of sky, each image a complex map of radio intensity, each map requiring human and machine inspection to identify and classify sources. It is, for much of the time, systematic and repetitive work. You build tools to automate the routine identifications. You develop pipelines. You look for what the pipeline flags as unusual. And sometimes, in the data, there's something the pipeline doesn't know what to do with. Something that doesn't fit any category. The software raises a flag. A human looks at it. And on a seemingly ordinary day in 2019, that human was Ray Norris, and the thing that didn't fit any category was a perfect circle glowing in radio waves. What do you do in that moment? Your first instinct, as I mentioned, is skepticism, but Norris is experienced enough to know what instrumental artifacts look like. And this didn't look like any artifact he'd seen. It looked real. And it looked new. He brought it to his colleagues. They checked it against every known category. Nothing fit. They pointed Meerkat at it. It was still there, consistent, real. They looked in optical catalogs. Nothing at that position and size. X-ray archives. Nothing. Infrared surveys. Nothing. And then they started looking more carefully at the rest of the ASCAP data. And they found more. This is the part of the story I find most human. Because the discovery of ORCs wasn't a single eureka moment. It was a gradual, careful process of verification, comparison, doubt, more verification, and eventually the acceptance that something genuinely new had been found. It took months between the initial spotting and the publication of the discovery paper. Months of checking, double-checking, reaching out to colleagues, building the case that this was real and not an error. This is what scientific discovery actually looks like. Not a single brilliant insight, but sustained, careful work by a community of scientists applying rigorous standards. Norris could not publish a paper saying underscore underscore quote underscore 6 underscore underscore without extensive verification. And the verification required not just Norris, but Meerkat operators in South Africa, archival astronomers checking optical and X-ray databases, theorists trying and failing to fit the observations into existing models. Science as a collective enterprise, distributing the work of verification across multiple independent teams and telescopes and archives. This is the system that makes scientific knowledge reliable. Not the genius of an individual, but the collective scrutiny of a community. Now let me tell you about something that happened after the initial paper was published that I think is genuinely remarkable. Because the discovery of ORCs didn't stay in the exclusive territory of professional astronomers, it spread. The field of radio astronomy has a tradition of citizen science, of involving amateur astronomers and members of the public in the analysis of telescope data. This tradition goes back decades to projects like Galaxy Zoo, which recruited hundreds of thousands of volunteers to classify galaxy morphologies in Sloan Digital Sky Survey images. Human pattern recognition, it turned out, was in some ways better than automated algorithms for certain tasks. People could spot things that machines would classify incorrectly or miss entirely. In the context of the EMU survey and ASCAP data, a citizen science project called Radio Galaxy Zoo was already operating, asking volunteers to help identify and classify radio sources in survey images. And when the news of ORCs spread, the citizen science community got engaged. Amateur astronomers began independently looking for ORC candidates in publicly available radio survey data. This cross-pollination between professional and amateur astronomy is one of the best things about the modern era of science. Data that previously would have been accessible only to specialists with the right computing resources and institutional access is increasingly available to anyone with an internet connection and the willingness to learn. And the ORC community has benefited from this openness. There's something deeply satisfying about the idea that right now, somewhere in the world, someone without a university affiliation is looking at radio survey data on their home computer and might be on the verge of finding the 9th confirmed ORC. It's not impossible. The data is there. The tools are increasingly accessible. The community is welcoming. Let me also talk about what ORCs tell us about the universe's past. Because when we observe an ORC, we are not seeing something happening now. We are seeing something that happened billions of years ago. The confirmed ORCs are located billions of light-years from Earth. Light and radio waves travel at 300,000 kilometers per second, the fastest speed anything can travel in the universe. At that speed, it takes light 1 year to travel 1 light-year. It takes light 1 billion years to travel 1 billion light-years. So when we observe an ORC that is, say, 4 billion light-years away, we're seeing the universe as it was 4 billion years ago. We're seeing an ORC in the young universe, when galaxies were different, more active, more gas-rich, forming stars at higher rates, merging more frequently than they are today. This is profound because it means the ORCs we're currently observing may not be representative of the ORCs that form in the modern universe. We're seeing ORCs from an earlier cosmic epoch, formed under conditions that no longer exist. If ORCs are driven by starburst events, and starbursts were more common in the young universe, which they were, then ORCs may be more common in the distant early universe than they are nearby. And our current telescopes, which can detect ORCs billions of light years away, but only in the most extreme examples, are giving us a biased sample. The SKA, with its much greater sensitivity, will be able to detect fainter ORCs and will find them at a range of distances. This will allow astronomers to trace how the ORC population has evolved over cosmic time, whether they were more common in the early universe, whether they're becoming rarer as the universe ages and galaxies become less active, or whether the rate of ORC formation has remained roughly constant. That kind of temporal information, understanding how a phenomenon evolves over cosmic history, is exactly what distinguishes a superficial understanding of an object from a deep one. It's the difference between knowing what something is and knowing why it exists. Let me bring this back to the larger picture. Because ORCs are not just a curiosity, they are a window. Every new phenomenon we discover in astronomy is a window into some aspect of the universe's physics or history that we hadn't previously been able to access. Pulsars, when discovered in 1967, became windows into the physics of extreme matter and the behavior of magnetic fields at intensities never before achievable. Gamma-ray bursts, once they were understood, became windows into the final moments of the most massive stellar deaths and into the early universe where they were more common. Fast radio bursts, still being understood, are windows into extreme events, magnetar flares, possibly, in distant galaxies, as well as probes of the intergalactic medium through which they travel. ORCs are windows into the energetic lives of massive galaxies, into what happens when a galaxy undergoes an extreme event, a starburst, a black hole merger, some other energetic occurrence, and releases enormous amounts of energy that propagate outward into the surrounding intergalactic space. They are records of galactic violence, written in radio waves across millions of light-years of space. And reading those records will tell us things about galaxy evolution that we can't currently access in any other way. How often do galaxies have extreme events? How much energy do they release, and in what form? And how far does it propagate? How does the release of energy from a galaxy affect the gas around it? And how does that, in turn, affect future star formation? These are some of the most important questions in galaxy evolution, and ORCs may be the best observational probe we have to answer them at the most extreme end of the energy scale. There's also a personal dimension to the ORC story that I want to acknowledge. Ray Norris, who found the first ORC, is an astrophysicist who has spent his career building radio telescopes and conducting radio surveys. He has contributed enormously to our understanding of radio galaxies, to the development of ASCAP and the EMU survey, to the infrastructure that made the discovery of ORCs possible. And finding something genuinely new, something that has no precedent in the scientific literature, something that requires a new name because it belongs to no existing category, is an experience that comes to very few scientists in their careers. Most scientific work is important, but incremental. It adds to the existing body of knowledge, refines existing models, tests existing predictions. True first discoveries, moments when you can say underscore underscore quote underscore 7 underscore underscore are rare. And when they happen, they mark a boundary in the history of science. There is a moment before the ORC was known, and a moment after. And that before and after has a name: Ray Norris, 2019. I find it genuinely moving that in the 21st century, after decades of intensive study of the radio sky with increasingly powerful instruments, there were still things waiting to be found that completely defied expectations. That the universe still had tricks up its sleeve, phenomena that our best theories hadn't anticipated. That the history of astronomy has not entered a phase of merely filling in details, but is still capable of producing genuine surprises at large scales. The universe is not finished with us. We are not finished with the universe. And the next ASCAP image that contains something that doesn't fit any category is already sitting in a data archive somewhere, waiting for the right person to look at it. That's the thing about astronomical discovery in the era of large surveys. There's more data than any single team can fully examine. The EMU survey alone will produce images of millions of sources, and ASCAP generates data at roughly 100 trillion bits per second. No one can look at all of this. Automated pipelines handle the bulk of it. Machine learning algorithms classify sources at scale. But the algorithms can only recognize what they've been trained on. The genuinely new things, the objects that fit no known category, are the ones that get flagged as anomalies, passed to human inspection, and occasionally turn out to be something nobody has ever seen before. The next ORC is probably already in someone's data. The next category of unexplained cosmic object might be flagged in a survey image that nobody has carefully examined yet. The universe's next surprise is waiting, and we are going to find it, because that's what we do. This has been Void Atlas. I'm your host. Thank you for spending this time with me at the edge of what we know. ORCs are a reminder that the universe is stranger than any of us imagined, and that the process of understanding it, slow, careful, communal, honest, is one of the greatest things our species has ever undertaken. 8 rings, 1,000,000 light-years across, invisible to every telescope except those that listen to radio waves, waiting in the darkness between galaxies, glowing faintly, keeping their secrets for billions of years before we finally built the instruments to see them. We see you now. Subscribe to Void Atlas. Come back next week. There's always more universe to explore. I'll see you out there, somewhere in the extraordinary mystery of everything. There's one more thing I want to explore before we close. Something that takes us from the specific mystery of ORCs into a broader question about the nature of discovery itself, and about what it means to live in an era when the universe is still revealing new things. We are at a peculiar moment in the history of astronomy. On one hand, we have more data than ever before. The surveys of the modern era, ASCAP, MEERKAT, the Very Large Array Sky Survey, LOFAR's All-Sky Survey, the Vera Rubin Observatory's 10-year Legacy Survey of Space and Time beginning operations, the Square Kilometer Array coming online. These projects collectively represent an avalanche of information about the universe. In the next 10 years alone, we will catalog more individual astronomical objects than in all of recorded history combined. And yet, paradoxically, the more we look, the more we find things we didn't expect. The history of astronomy is not a story of progressively smaller surprises. The surprises get bigger as the instruments get better. Because better instruments see fainter things, more distant things, things at wavelengths we couldn't previously access. And at every new sensitivity threshold, at every new wavelength, the universe has something unexpected waiting. ORCs are a perfect example. They weren't found by building a telescope specifically designed to look for them. They were found by building a telescope designed to survey the radio sky in general, at greater sensitivity than any previous survey. And the greater sensitivity revealed something that lower sensitivity surveys had missed entirely. Something that, in retrospect, was probably always there. The radio emission from these enormous structures was too faint for older instruments to detect, but was invisible to us until the technology caught up. This pattern repeats throughout astronomy. Quasars were discovered when radio astronomers mapping the radio sky in the 1950s and 60s found radio sources that optical astronomers then identified with point-like objects that didn't look like galaxies. Strange, compact, incredibly luminous. They turned out to be the most energetically active objects in the universe. Supermassive black holes consuming matter at prodigious rates in the distant young universe. Nobody predicted quasars before they were found. No theory said, quote, 8, quote. They emerged from the data. Gamma-ray bursts were discovered by military satellites monitoring the Nuclear Test Ban Treaty in the 1960s. The Vela satellites, designed to detect the gamma-ray flash from nuclear weapons tests, started detecting brief gamma-ray pulses from random directions in the sky. The military quickly determined these weren't from Earth or the solar system. They were coming from far beyond. The discovery was declassified and published in 1973. Nobody predicted gamma-ray bursts. They were a byproduct of technology built for a completely different purpose. The cosmic microwave background, the most significant cosmological observation of the 20th century, was discovered when Penzias and Wilson couldn't explain why their antenna was noisier than it should be. They tried cleaning pigeon droppings off the antenna. They checked every possible source of noise and eventually concluded that the noise was coming from the universe itself, that they were detecting the leftover radiation from the Big Bang. Nobody handed them a grant to go find the CMB. They stumbled into it. ORCs fit this pattern perfectly. They are one more chapter in the long story of the universe surprising us, of instrumentation revealing what theory hadn't predicted, of data containing things that don't fit the categories we've built. And I find this pattern not just intellectually interesting, but genuinely encouraging. It means the universe is not yet transparent to us. It means there are still large-scale phenomena occurring at cosmic scales that we haven't identified, haven't named, haven't fit into any framework. It means the project of understanding the universe is very much ongoing. Not in the sense of filling in fine details, though that matters too, but in the sense of discovering entirely new chapters that weren't known to exist. What will be found when ASCAP's full EMU survey is complete? What will Meerkat find as it continues its deep radio imaging programs? What will the SKA discover in its first year of operation? What completely new categories of object will require new names because they don't fit anything we currently know? I genuinely don't know. No one does. And that's the point. The universe has a long history of surprising us, and there's no reason to think that history is over. But I know this: the people who will find the next ORC, the people who will look at a radio image and see something that doesn't fit any known category, are the people who are building telescopes right now. Calibrating antennas in the Western Australian outback, processing petabytes of survey data on supercomputers in South Africa, writing software pipelines that flag anomalies for human inspection, reviewing those anomalies one by one, skeptically, carefully, honestly. The next chapter of the universe's story is being written right now, in the unglamorous daily work of modern astronomical surveys. And somewhere in that work, there's a moment waiting. A circle that shouldn't be there. A signal that doesn't fit any category. A first look at something the universe has been keeping to itself, waiting for us to build the right instrument, pointed in the right direction, sensitive enough to finally see. We are in the golden age of radio astronomy. We are at the beginning of an era of enormous all-sky surveys. We are building instruments that will change everything we know about the radio universe. And we are already, with ASCAP alone, finding things that nobody predicted and nobody can fully explain. This is the best possible time to be paying attention to what the universe is telling us. The messages are arriving faster than ever. The instruments are more sensitive than ever. The data is more accessible than ever. And the universe, as always, has more to say than we've yet learned to hear. 8 rings. 1,000,000 light-years across, no known explanation, and the SKA on its way. I cannot wait to see what we find. This is Void Atlas. I'm your host. Thank you for being here. Thank you for caring about the things we don't yet understand. Thank you for the curiosity that makes this kind of exploration possible and worthwhile. Subscribe. Come back next week. There's always something new at the edge of what we know. Until then, keep wondering. The best discoveries haven't happened yet.